In the name of God, welcome back. During the last video, we've talked about Boltzmann distribution. We have derived this relationship, probability of having a thermal system in some energy epsilon is directly proportional to exponential minus epsilon divided by kBt. Kb is the Boltzmann constant, T is the temperature of the system. We've also derived, excuse me, Maxwell-Boltzmann distribution. So applying Boltzmann distribution to a system of gas, of molecules, the speed of a molecule v, so the probability density of finding a molecule with velocity or with speed between v and v plus dv is given by this relation, which is PV is directly proportional to v squared times e to the minus mv squared divided by 2k bt. Kb is Boltzmann constant again, T is the temperature, m is the mass of the molecule. Today I would like to make some illustrations of the Boltzmann distribution and hopefully write some code. So we consider a system of, let's say, having a 20 by 20 grid system. On each side of the grid we can arrange some quanta of energy. So each side can accommodate a quantum of energy, and we have the initial state of the system to be in such a way that all sides are filled with a unit of energy. So there is one quanta of energy in these sides, all of them. In total, there's going to be 400 sides arranged in the 20 by 20 grid. And excuse me, for this initial state, we can show a histogram in this way. So here in the horizontal axis, we have number of quantum. And on the vertical axis, we have number of sides having so number of sides having the quantum under consideration. The setting is such that on each side we can either have 0 quantum or 1 quantum. Okay. So for the initial state, the histogram is going to be something like that. No side is having 0 quantum, but all the sides, and their number is 400, have 1 quantum on it. Right. So the number of possible ways of having this initial state can be computed using the combinatorial NCR, and you can find that there is only one way of having all the sides to be filled with one unit of energy. Okay. So here it means omega is going to be equal to 1, okay, for the initial state. We're going to say update the initial state. So if we have updates, the update is going to be as follows. One chooses a site randomly. So let's say from the initial state, I randomly choose a site. Yeah. And so here it has 1 quantum. I remove the 1 quantum so that it becomes 0. and I moved the one quantum into another random site. So some other random site, initially it's 1 because the initial state we have all sites filled with 1. So I'm going to change this randomly chosen second site, and then I add 1 to it. Okay, so at the end of this update, the first iteration of the update here, it's going to be 0 quantum, and then here it's going to be 2 quantum. So this is one iteration of the update. And then in that way we can see that let's say we're going to have then something like this. It's going to change, histogram is going to change, it's going to become boom in black to represent like 399 sites having 1 quantum, and then like here it's going to change. I'm going to have 1 site with 1 quantum. So the black means after first iteration of update. Okay, so you can see that here the updated state is a new state, right? And one can think of the number of possible ways of reaching that state. Okay, so you can compute omega for the updated state. Actually it's going to be equal to, so to begin with, in choosing the first random position, there are 400 possibilities because there are 400 sites, and I'm just going to choose one of them randomly. So we're going to have let's say omega for iteration number, first iteration is going to be equal to 400. So there are 400 possible ways of choosing a site where I remove the quantum there, so it becomes 0. And then there are 399 possible ways of putting the selected quantum into another new site. Okay, so the total possibilities is going to be 400, let's say, times 399. Okay, so you can see that the initial state with just 1 microstate is much less probable in terms of probability compared to this updated state omega 1 with 400 times 399 possible ways of having such arrangement. So the arrangement is I have 1 site having 2 quanta, 1 site having 0 quanta, and the rest of the sites would have 1 on it. Okay, so one can repeat these updates, updates some number of times. So let's say number of iterations, you can choose it to be iterations to be, let's say, 1000 or 10,000. And at the end of the day, we're going to have a histogram, and the histogram is going to be like Boltzmann distribution. So if we choose number of iterations to be large enough, then what we're going to have some histogram which is behaving in an falling, decaying, exponential manner. Okay, so we're going to have the number of sites with 0 is going to be most, number of sites with 1 is less, number of sites with 2 quanta, with 3 quanta, with 4 that way. And the aim is one can write a code to simulate what I have just explained. And we can take a look at that. So this is a code which is written for what I have just explained. You can spit out this code using some large language model to make a Python code for you, or whatever programming language you want to use. I have done so here using Python as the programming language. So it's based on NumPy and Matplotlib. So when you import those, and the grid side here, we're going to have a grid with 20 sides. So in 2 dimensions is 20 by 20, and the number of iterations for making updates, I've chosen it to be 1000. So this is setting up this part from line 9 to 12 is setting the figure. Okay, line 14, 15 is for initializing. So the initial state, we're just going to have ones inside the 2-dimensional grid, 20 by 20 grid. So grid side is 20. Okay, defined earlier. It's going to be some sort of animation, and that's why I'm using this Matplotlib animation as animation here. And animation, you can see how it works. It needs 2 methods to be defined. We're going to give the animation function, which is called func animation. We're going to give it an object for the figure. We're going to have a method which updates the figure, right? And down here, let's see, we're going to have an initialization. So the initialization is going to be given by this init function. So 2 methods are defined upstairs. One is init, and the other one is like this update. Okay, and let's take a look at the init. The init function is defined here, line 46. Okay. So the initial distribution is going to be plotted. So we have a grid, we have a title for the plot, we have the energy levels and the counts, okay, which is going to be this unique method applied to the grid. Grid is defined earlier. Let's see, grid. You can see grid is here, initialized earlier, where we have ones on all sides, right? And so we have the levels for the plots and the title. Okay, and then there is the method for making updates, and it's going to need the grid variable. So it's global grid is being used inside the function, right? And here 2 points are selected randomly. So x1 and x2 is like the initial point. We choose where we decide to remove a quantum if we have a quantum there. If there isn't a quantum there, so we just leave it as it is and we look for another site, because the setting is such that each site can have 0 or 1 initially. Okay, and during like the iterations of the updates, the number of Quanta should always be 0 or something positive, an integer. Anyway, so this random a random point is selected for removing, and then another random point x2 y2 is selected for putting for updating, adding the quantum there, and the transfer is done in this block. So if actually what is on the side is greater than 0, then we remove one quantum from x1 and y1 and add one quantum to x2 and y2. So x2, y2 again is the destination. x1, y1 is where we remove a quanta. Okay, and this works nicely. Let's see, I hope, yeah, so you can see how it evolves. Maybe let me make this bigger. Okay, this is showing iterations of energy transfer, and the number of iterations chosen here in this example is 1000. So you can see as the iterations progress, really the histogram is taking a shape, is taking an exponentially decaying shape somehow. Okay. Yeah, so you can see the horizontal axis is the energy quanta, so, and the vertical axis number of sites. So this histogram in blue is showing number of sites with 0 quantum, number of sites with 1 quantum, number of sites with 2 quanta, number of sites with 3 quanta, that way, so on. I think it has finished, and I think one can see even by eye that this is an exponentially decaying kind of a histogram feature. So you can see this is actually a Boltzmann distribution. In a way, one can like simulate temperature in this way, temperature or energy. So the higher the energy, the higher the temperature is. We can increase the energy of the system by assuming that initially, instead of having one quanta on each side, we can have a case where we have, let's say, 2 quanta on each side initially. Okay, and the process of updating remains the same. So one can see that like the number of quanta of energy is much bigger, right, compared to the situation where we have only one on each of the sides. Yeah. And we can make a simulation of these two beside two systems beside each other to see how it's going to evolve. There is an so here we have two grids, grid number 1 and grid number 2. Grid number 1 at the initial stage has ones in it everywhere. Grid number 2 we have 2 quanta, so this is 2 times ones on each side of the grid. And for the figure we're going to show, there are going to be 3 plots. Okay, the first 2 showing the 2 grids, and the third one to show the histograms of the system as it evolves. Let me try to run this. Let's see how it goes. So I can pause it. So this is the initial state. Hopefully you can see this. Is it possible to make it bigger? Looks somehow. On the left is system number 1, so grid number 1, so 1 quanta initially on each side. So we have 20 grids by 20 grids. Okay, And you can see the color bar here, which represent number of quanta per side. You can see it's yellow, and yellow is really 1. So on each point on the grid, we have 1 quantum on it. Yeah, it's going here. My mouse changed it, sorry. The second grid, we have 2 initial quanta on each side. So you can see the color again, it's more darker yellow. So on each side there's going to be 2 quanta of energy. And on the third plot there is a histogram. So histogram, you can see for the initial state, the blue histogram represents grid number 1 or system number 1, and the yellowish orange kind of histogram is for grid 2, system number 2. And you can see that for the blue one we have 400 sides. So number of sides is the vertical axis. There are 400 sides, all of them have 1 on it. For the second grid, we have 400 sides with 2 quanta on it. If I release unpause the animation, then updates are going to be made, and it's going to change and progress with time. Boltzmann distribution. Here the aim is just to sample, so this is adapted from the sci-fi documentation for sampling from some particular probability distributions, right? So here there is a class Boltzmann distribution. So this is the probability density function. It's a function of p, so it's like that, exponential minus p. So here we take the Boltzmann constant to be equal to 1 for simplicity. Temperature here is 100. Okay, you differentiate the probability density function. Is this method the PDF? The reason is we're going to use this transformed density rejection method, which is in sci-fi stats sampling. And you can see it requires a distribution, and the distribution is generated here. It's the Boltzmann. Oops. It's the Boltzmann distribution. Okay, and we can generate some random numbers that will be changed to distributions over Boltzmann, and we can we can generate random samples here. This is generating 1000 random samples drawn from Boltzmann distribution. And here I wanted to kind of compare what we get from the sample with respect to the exponential distribution function. Okay, and we can plot them to see here. Let's run this to see what's going on. Okay, yeah, so you have something like that. Okay, so this is the histogram, which is made, let's say in blue, from the sample of points numerically drawn. So this is sample from Boltzmann distribution. Yeah. And red is kind of the true Boltzmann distribution. So you can see it agrees. Actually, it's exponentially falling. Okay. That's it. I think you can download these codes in the link I'm going to provide below and play with it. And I think that's it for today. showing some codes, playing with Boltzmann distribution. Take care, and I will see you next time.